One of the most surprising claims circulating in collector and investment circles right now is that the planet's most expensive mineral by far isn't a sparkling gemstone at all.
Which, completely flips the script on how we've been taught to think about wealth.
Right. Because, I mean, welcome to the deep dive, first of all. But yeah, you picture a Swiss bank vault stuck to the ceiling with gold bullion, or maybe a flawless, blindingly clear diamond, right, resting on a velvet pillow in a museum.
Exactly. That's the Hollywood image.
But right now, automotive engineers are agonizing over a dull, powdery, silvery metal that just completely dwarfs the price of all of that, and your car simply won't start without it.
Yeah, we have this deeply ingrained, almost mythological understanding of wealth. We've been conditioned over centuries, through folklore and pop culture, to believe that the ultimate expressions of earthly value are always things we wear on our fingers or lock in a display case.
Right, the shiny things.
Exactly. But the data tells a remarkably different story about what actually drives value in the modern world.
And that is exactly our mission today. We are taking a massive stack of sources, and I mean massive. We've got the latest highly detailed USGS mineral commodity summaries, the Rarest precious metals forecast for 2026, some really fascinating bulletins from the Mineralogical Society of Southern California, and historical gemstone auction data.
It's a lot of data to sift through.
It is. And we are completely deconstructing the true value of the Earth's rarest materials for you.
Because when you lay all of these sources out and actually look at the underlying data, you quickly realize we are dealing with two entirely distinct parallel universes of mineral wealth.
Yeah.
On one side of the ledger, you have the aesthetic, purely emotion-driven gemstone market. And on the other side, you find the utilitarian, relentlessly industry-driven metals market.
And we are going to act as your neutral science and market communicators today. We really want to explore the mechanics of why things cost what they do.
Yeah.
And I want to make it incredibly clear right up front, there is no investment hype here.
None at all.
No flashy sales pitches, and absolutely no financial advice. We are just looking at the raw geology, the complex chemistry, and the cutthroat economics of the rarest materials on Earth.
Right, because the physical mechanics behind why a certain rock or, a particular gram of metal is worth millions of dollars, that's infinitely more fascinating than the price tag itself.
Oh, absolutely.
The underlying physical reality dictates the economic reality. If you don't understand how the earth cooked the material or how an engineer actually applies it, the price tag is just a meaningless number on a screen.
Totally. So let's start on the traditional side of that spectrum, the $1 million per carat club.
The fun stuff.
Right. If I ask you, the listener, to picture the single most expensive gem in the world, your mind probably jumps straight to a diamond or maybe a massive ruby. But the current record holder, like the absolute apex predator in the gemstone world, is Jadeite.
Yeah, Jadeite.
It commands prices up to $3 million per carat.
That is a figure so astronomically large that it actively defies our ability to visualize it without some serious grounding.
Right, so let me build a visualization for you then. Because a single carat is incredibly tiny.
Extremely tiny.
It weighs just 0.00643 ounces. We're talking about a fraction of an ounce here. So if we run the math on $3 million for that microscopic weight, one single carat of top-tier jadeite can rival the worth of roughly 926 standard 1-ounce gold bars.
Wow. That comparison really highlights the absurdity of the market, doesn't it?
It really does.
You are taking a pebble-sized piece of this mineral, something you could lose in the fabric of your car seat, and equating it to a literal mountain of gold.
Yeah, and look at the auction data from the late 1990s. There was a specific jadeite jewelry item, the famous doubly fortunate necklace, that sold at Christie's for $9.3 million.
Incredible.
So my immediate hurdle here is trying to understand the physical origin. How does the Earth bake a rock that eventually becomes worth 926 gold bars per carat?
Well, the creation of jadeite really comes down to the Earth acting as an incredibly precise, incredibly unforgiving pressure cooker.
Okay, a pressure cooker.
Right. If we look at its chemical composition, jadeite is a pyroxene mineral. It's fundamentally made of sodium aluminum silicate. But the trick is, you can't just throw sodium, aluminum, and silicate into a standard volcanic magma chamber, turn up the heat, and expect to pull out jadeite.
You can't just melt it together.
No, the planet requires highly specific, almost contradictory geological conditions to fuse those elements in that specific crystalline structure.
I want to pause on the word contradictory. How can geological conditions be contradictory? Do you mean it needs to be hot and cold at the same time?
In a sense, yeah, actually. Jadeite forms almost exclusively within subduction zones.
Subduction zones.
Right. To visualize a subduction zone, you have to look at the macro scale of the Earth's crust. Imagine two of the planet's massive tectonic plates slowly colliding.
Okay, I'm picturing it.
The sheer force of that collision forces one plate to bend and plunge underneath the other, driving it deep down into the Earth's mantle.
So we have billions of tons of rock grinding against billions of tons of rock, pushing downward.
Exactly. The pressure is truly apocalyptic. Now, standard geological intuition tells us that as you go deeper into the Earth, the temperature skyrockets.
Right. It gets hotter the closer you get to the core.
Exactly. And that extreme heat is how we get standard volcanic minerals. They melt and reform. But jadeite is incredibly finicky. It requires that astronomical pressure from the crushing weight of the tectonic plates, but it demands relatively low temperatures.
Wait, so it needs to be crushed beyond belief, but it absolutely cannot be melted.
Yeah, that is the geological paradox, yeah. If the temperature in that subterranean environment gets even slightly too high, the chemical bonds within the sodium-aluminum silicate alter, and the resulting formation is a completely different, drastically more common mineral, something like augite.
Oh, wow.
So the subduction zone provides this incredibly rare geological Goldilocks zone.
Not too hot, not too cold.
Precisely. The pressure from the tectonic collision is immense, but the surrounding cold oceanic rock that is being dragged down insulates the reaction zone just enough to keep the ambient temperature down.
Okay, but I am looking through the sources, specifically the mineralogical data, and I need to throw a wrench in this narrative for a second.
Go for it.
The documentation says jadeite can be found in places like California, Japan, Russia, Kazakhstan, Guatemala. If this material is found scattered across all these different countries, why is the price so astronomically high? I mean, I could probably drive out to a specific fault line in California right now, hike around with a rock hammer, and find some, right?
You absolutely could, yeah, and geologists do. But we have to draw a massive, incredibly thick line between chemical jadeite and what the market actually values.
Okay, explain that.
What you would find in a creek bed in California is, strictly speaking on a molecular level, jadeite. But the international auction market is not paying $3 million a carat for just any rock with that chemical signature.
Right.
That valuation is reserved exclusively for imperial green jadeite.
So there's a hierarchy within the mineral itself.
Oh, a remarkably steep one. The vast majority of the world's truly top-tier gem-quality imperial green jadeite does not come from California or Guatemala. It comes from one highly specific, violently contested geological pocket,
Which is?
the H-Peket mines in northern Myanmar.
Okay, so if the California jadeite and the Myanmar jadeite are baked in similar tectonic subduction zones, what makes the H-Peket oven so special?
It comes down to trace impurities injected at the exact right moment of formation.
Impurities.
Yeah, the subduction zone beneath the H-Peket region had the exact right trace elements, specifically a heavy dose of chromium flushed into that high-pressure, low-temperature crucible millions of years ago.
And what does the chromium do?
That chromium substitutes for aluminum in the crystal lattice, creating a deep, vivid, almost aggressively luminous green. But more importantly, the structural formation in that specific region allowed the stone to become semi-transparent.
So it's not just a solid rock.
Right. Light actually penetrates the surface and glows from within. It possesses a visual depth that outshines even the finest Colombian emeralds.
So we have this extreme geological scarcity, a specific tectonic collision, a specific temperature balance, and a specific injection of chromium. But that only explains why it looks pretty.
Sure.
It doesn't fully explain the multi-million-dollar price tag.
Yeah.
There has to be a psychological element here, right?
Oh, absolutely. You have to layer thousands of years of profound cultural significance on top of that geological rarity.
Like what?
Well, the sources outline its roots in ancient Mesoamerica, where the Olmecs and Mayans valued it above gold, but its primary, overwhelmingly dominant buyer market today is China.
And in Chinese culture, jade is practically a deity in mineral form, isn't it?
It really is. It is deeply entrenched in the societal DNA. For centuries, the finest jade has been inextricably tied to royalty, spiritual purity, and good fortune.
Wow.
Confucius actually famously compared the physical qualities of jade to the moral virtues of a gentleman.
Oh, right.
Yeah, he said its smooth polish represents benevolence, its dense structure represents intelligence, and its sharp but uncutting edges represent justice.
That's beautiful.
It is. So you are looking at a perfect economic storm here. Extreme geological scarcity of the imperial green variant, colliding with an inelastic, deeply ingrained, multi-billion-dollar cultural demand.
So it basically functions as the ultimate undeniable status symbol.
Exactly.
But if you are listening to this and thinking about navigating the jade market, you have to tread incredibly carefully.
Very carefully.
Because the sources emphasize a massive, treacherous gulf between the verified historic auction records for these specific imperial pieces and the general market hype for lower-grade stones.
You'll see a lot of junk out there.
Right. You will see tourist crafts and online vendors pushing rare jadeite that is chemically treated, dyed, or is simply a low-grade offshoot that is essentially worthless on the secondary market.
And that is the inherent danger of participating in the emotional gemstone market. The entire concept of value is anchored to human perception of color and cultural storytelling. We actually see an identical phenomenon when we analyze the market data for red diamonds.
Oh, the auction data on red diamonds is staggering.
Wow.
We are talking about valuations reaching $2 million per carat.
Yeah.
And what fascinates me is how they get their color. Because if I look at a pink diamond or a blue diamond, that color usually comes from a chemical impurity, right? Like boron or nitrogen sneaking into the carbon structure.
Usually, yes. A trace element acts as a coloring agent. But red diamonds completely defy that logic. Their crimson color is not born from a chemical impurity. It is born from structural trauma.
Structural trauma. I love that phrase.
It is really the most accurate description. Red diamonds get their color from severe structural anomalies within the crystal lattice itself.
How does that happen?
Well, during the diamond's formation deep within the Earth's mantle, or during its violent volcanic journey to the surface, it undergoes enormous uneven pressure. This pressure actually forces the layers of carbon atoms to slip out of alignment. Geologists call this clastic deformation or gliding atoms.
So the extreme pressure essentially bruises the diamond, and because of that microscopic bruising, we humans decide to pay $2 million a carat for it.
Exactly. That deformity alters how light travels through the carbon structure. It absorbs certain wavelengths and transmits that specific incredibly rare crimson hue that the human eye finds spectacularly beautiful. We are placing a massive financial premium on a geological defect.
That is wild. And that concept forces a pivot in how we analyze this data.
How so?
Well, if extreme rarity and specific visual anomalies drive the price of imperial jadeite and red diamonds, what happens when the underlying premise, the very definition of rare, is suddenly flipped upside down?
Oh, I see where you're going.
Right. We move away from stones valued for their cultural resonance or their color, and step into a market where stones are valued purely for the math of their scarcity.
And there is no case study in modern mineralogy that illustrates the danger of that mindset better than the story of Painite.
This story reads like a thriller for geologists. Let's set the scene. It's the early 1950s in Burma, which we now call Myanmar.
Right.
A British mineralogist named Arthur C.D. Payne is exploring a remote gemstone field near a small village. He is sifting through alluvial gravel, basically riverbed material, and he finds a single tiny dark red crystal.
Just one.
Just one. It weighs just 1.7 grams.
Yeah.
He examines it, tests its refractive index, and realizes he has absolutely no idea what it is.
Which is saying something for a mineralogist.
Right. So he recognizes it as something completely foreign to known mineralogy, so he does what any good scientist would do, and donates it to the British Museum of Natural History in London for extensive study. And in 1957, after years of analysis, the scientific community officially recognizes it as a brand new mineral species, and they name it Painite in his honor.
And from that moment on, Painite became legendary.
Oh, absolutely.
For a very long time, it literally held the Guinness World Record for the rarest gemstone mineral on the entire planet.
The statistics from that era are almost unbelievable to me.
Yeah, for nearly a quarter of a century after its initial discovery, only 2 crystals were known to exist in the entire world.
Pew-pew.
Just 2. And both of them were sitting in the vaults of the British Museum.
Think about the psychological weight of that.
Yeah.
Billions of tons of rock on Earth, and we only have 2 tiny fragments of this material.
It's mind-blowing.
By 1979, a tiny third fragment was identified in a parcel of rough gems. But still, the narrative was locked in. Painite is the rarest material on Earth. And because of that narrative, the per-carat valuation in collector circles was astronomical. It floated somewhere around $50,000 to $60,000 a carat.
Right.
But that price wasn't because it was uniquely beautiful or culturally significant like jadeite. It was driven entirely by the ego-driven allure of possessing something that literally no one else on the planet had.
That narrative held absolute power over the market until the year 2002.
The ultimate geological plot twist.
Yeah.
In 2002, George Rossman, who actually wrote the piece for the Bulletin of the Mineralogical Society of Southern California that we were referencing, takes a trip to Myanmar. He visits a gem market in a town called Namia.
Okay.
He finds a local vendor selling a little canvas bag of rough, uncut stones.
Okay.
Rossman pays $10 for the bag, 10 American dollars.
Oh.
He assumes the bag is full of standard, low-value spinels and zircons. But when he gets back to his lab and runs the spectroscopy, well, he unknowingly purchased 2 painite crystals.
And that seemingly trivial $10 transaction triggers a massive paradigm
It
shift.
changes everything.
Rossman immediately relays this discovery to his geological contacts back in Myanmar. He tells them, I found these in a parcel from Namia. You need to look closer at the rough coming out of that region.
And this is where the science takes the wheel. By 2005, researchers in Pasadena start studying the microscopic inclusions, the tiny trapped minerals inside these new painite crystals.
Right, looking for clues.
Exactly. They're looking for clues about how it formed, and they realize a massive mistake had been made for 50 years. Everyone thought painite formed in standard alluvial gemstone fields, but the inclusions pointed to an entirely different geologic environment.
They pointed to skarn deposits.
Yes. I need you to break down the mechanics of a skarn deposit, because the moment they realized this, the entire market collapsed. What is happening inside a skarn deposit?
Well, a skarn deposit is a highly volatile metamorphic zone. Imagine a massive chamber of superheated magma pushing its way upward from deep within the Earth's crust.
Okay, magma pushing up.
Now imagine that magma chamber comes into direct contact with a layer of carbonate rock, specifically something like limestone.
Oh, wow.
The extreme heat from the magma, combined with super pressurized, mineral-rich fluids escaping from the magma, basically pressure cooks the surrounding limestone.
So it's not just melting the rock, it's chemically attacking it.
Exactly. It forces a massive, chaotic exchange of elements. The limestone breaks down, and a highly specific chemical cauldron is created. In the case of painite, you had boron, calcium, aluminum, and zirconium all swirling together in this superheated, fluid-rich contact zone.
Wow.
For 50 years, humans were looking for painite in the dirt of riverbeds, assuming it was formed like a standard ruby. Once geologists realized it was formed in skarn deposits, they changed their search parameters.
They looked in the right place.
They stopped looking in the gravel and started looking for actual rock outcrops where ancient magma chambers had intersected with limestone.
And the result of that shift in perspective was instantaneous. Within weeks of identifying the correct geological formation, prospectors found the actual rock outcrops in Myanmar. Within months, hundreds and eventually thousands of painite crystals flooded the global market.
The total known population of this world's rarest mineral went from 3 single crystals
Just 3.
to thousands of them, seemingly overnight.
I love trying to find an analogy for this. Imagine you are a collector, and you pay a massive, life-altering fortune for a supposedly one-of-a-kind mint-condition comic book.
Okay.
You put it in a vault, feeling secure in your investment, and then the very next day, a construction crew knocks down a wall in an abandoned warehouse and discovers 10,000 pristine copies of that exact same comic book.
Ouch.
Right? The value of your comic, which was based almost entirely on the idea of unrepeatable scarcity, plummets to the floor.
The painite crash perfectly illustrates the inherent danger of treating the aesthetic mineral market as a stable store of value. Scarcity, when used as a financial anchor, is incredibly volatile. If you are analyzing these markets, you must understand the fundamental difference between macro-rarity and micro-rarity.
Let's expand on those definitions, actually. Walk me through the difference.
Sure. Macro-rarity is an absolute truth of planetary physics. It means a specific mineral is geologically scarce everywhere on the planet, full stop.
Right.
The actual elemental ingredients simply do not exist in large quantities in the Earth's crust, or the planetary conditions required to fuse them, like the subduction zones for jadeite, are virtually non-existent.
Got it. And micro-rarity.
Micro-rarity, however, is a human illusion. It means the mineral might actually be somewhat abundant in a specific localized geological formation, but we simply haven't pointed our shovels at the right rock formations yet.
So painite was the ultimate example of micro-rarity. We were panning in the river, completely ignoring the cooked limestone just up the hill.
Exactly. It was an illusion of scarcity born from a lack of geological understanding. And the terrifying thing for collectors is that we see this micro-rarity illusion propping up other ultra-rare gems right now. Look at the data for serendipite.
Serendipite is another fascinating case study. discovered in Sri Lanka in 1902. The sources note that up until 2002, a full century later, only two faceted gem-quality samples were known to exist.
And it carries a price tag around $1.8 million per carat.
Right.
It requires an incredibly complex multi-elemental collision to form. You need aluminum, calcium, boron, magnesium, silicon, and oxygen to all converge in specific metamorphic conditions. Or look at red beryl.
Well, a red beryl is primarily found in the United States, right?
Yes, almost exclusively within the topaz-bearing rhyolite of the Wawa Mountains in Utah.
The comparative rarity statistics on red beryl are wild. The documentation states there's only one red beryl crystal found for every 150,000 gem-quality diamonds.
That ratio is absurd.
It is, and it commands prices around $10,000 a carat. But you mentioned it forms in rhyolite. I want to make sure I understand the mechanism. What makes a rhyolite formation so unique that it traps this specific red crystal?
Well, rhyolite is essentially volcanic rock, often glassy, created by highly viscous, silica-rich lava. To get red beryl, you need a very specific chain of events. First, this thick volcanic lava erupts and cools. As it cools, it shrinks and forms fractures and cavities.
Okay, cracking rock.
Then, high-temperature gases rich in beryllium have to escape from the cooling magma below, travel up through those cracks, and react with oxidized surface water that is seeped downward.
Down into the cracks.
Right. And that surface water must contain dissolved silica, alkali metals, and specific iron-manganese oxides to give it the red color.
So it's an incredibly delicate dance between volcanic gas, cooling rock, and contaminated groundwater.
A delicate dance that rarely happens. But the lingering risk, the shadow hanging over anyone holding serendipite or red beryl as a store of value, is the Painite precedent.
That someone might just find a whole bunch of it.
Tomorrow morning, a geologist in a completely different part of the world could discover a massive untapped skarn deposit or a massive hidden rhyolite vein, and that multi-million-dollar scarcity premium vanishes into thin air.
That terrifying volatility forces a major shift in our investigation, I think. Because a $3 million jadeite stone, or a nearly $2 million serendipite crystal, is only worth that much if a single wealthy human being agrees to buy it at auction. Its value is entirely subjective, propped up by ego, aesthetics, and cultural mythology. But what if we look at minerals whose value isn't based on human emotion at all?
Now we're talking.
What if we examine materials priced entirely by the relentless, high-volume, uncompromising demands of global industry? This loops us right back to the provocative hook we opened with.
Yeah, if we leave the velvet cushions of the auction houses and step onto the factory floors of global manufacturing, we meet a family of elements known as the platinum group metals, or PGMs.
PGMs.
If you look at the periodic table, this is a dense cluster of 6 specific elements: platinum, palladium, rhodium, ruthenium, iridium, and osmium.
And when we pivot from gemstone auction records to the pricing data from the USGS and the Rarest Precious Metals 2026 forecast, the numbers become incredibly sobering.
Very sobering.
Let's isolate rhodium. According to the Rarest forecast data, rhodium is currently trading somewhere between $6,000 and $9,000 per ounce. That breaks down to roughly $400 per single gram. But if we look back at its historical volatility, it hit an all-time peak of over $20,200 per ounce.
A valuation that completely shatters the price of gold, silver, or platinum.
To really drive this home for you, the listener, we were talking about a non-gemstone element. It is a dull, silvery white powder or solid metal. You cannot realistically forge jewelry out of it. It doesn't sparkle.
No, it does not.
Yet it commands $20,000 an ounce. The obvious question is, why? What can a gram of rhodium do that a $2 million red diamond cannot?
Its astronomical value is anchored entirely in unforgiving utilitarian necessity. Specifically, it is the linchpin of the global automotive industry. Rhodium is the undisputed, unparalleled king of the catalytic converter.
Let's pretend I know absolutely nothing about the internal mechanics of a car. I turn the key, the engine rumbles, I drive.
Yeah.
Why does my vehicle require thousands of dollars worth of this obscure silvery metal just to function?
Okay, let's break down the chemistry of driving. When an internal combustion engine burns a mixture of gasoline and air to create power, the combustion process is incredibly violent and imperfect.
Sure.
It creates a cocktail of very nasty chemical byproducts. The most dangerous of these are nitrogen oxides, commonly referred to as NOx gases.
These are the gases that essentially poison the atmosphere.
They are highly toxic. They are the primary atmospheric precursors to severe smog, acid rain, and massive surges in human respiratory diseases.
Oh, wow.
Because of this, environmental protection agencies worldwide have established incredibly strict, legally binding regulations limiting exactly how much noxic gas a car is allowed to emit from its tailpipe.
So enter the catalytic converter.
Right. The catalytic converter is essentially a chemical processing plant bolted to the underside of your car. It sits in the exhaust pipe between the engine block and the muffler. If you cut one open, you would find a ceramic honeycomb structure.
Okay, a honeycomb.
The walls of that honeycomb are coated with a microscopically thin wash coat containing platinum group metals. When the hot, highly toxic exhaust gases leave the engine and hit this honeycomb, the rhodium embedded in the coating acts as a chemical catalyst.
I want to make sure I define catalyst correctly in this context. It means it accelerates or enables a chemical reaction, but it doesn't actually get consumed by the fire. It facilitates the change without destroying itself.
That is the perfect
Okay.
definition, yeah. The rhodium facilitates the reduction of those toxic gases. As the nitrogen oxide molecules flow through the honeycomb, they bind to the surface of the rhodium. The unique electron structure of the rhodium violently rips the nitrogen atoms away from the oxygen atoms.
I picture the rhodium acting like a microscopic battering ram, just smashing the toxic molecule apart.
A battering ram, or perhaps a very aggressive chemical matchmaker.
Ah, right.
The rhodium holds on to those isolated nitrogen atoms until another nitrogen atom comes along. It forces them to pair up, forming N2 gas, which is completely harmless and makes up about 78% of the air we breathe every day.
Oh, that's brilliant.
It then releases the leftover oxygen atoms, so toxic gas goes in, harmless air comes out.
And the automotive engineers can't find a cheaper substitute. They are forced to pay $20,000 an ounce for this specific metal.
That is the crux of the market value. Rhodium is uniquely, profoundly gifted at the reduction of nitrogen oxides. Platinum and palladium, its sibling metals, are excellent at oxidizing other byproducts like carbon monoxide, but when it comes to tearing apart non-Higgs gases, rhodium has no equal on the periodic table.
None at all.
To give you a sense of scale, the USGS data from 2012 showed that a staggering 81% of all the rhodium mined on the entire planet went straight into manufacturing catalytic converters.
So the price isn't driven by desire. It is driven by regulatory hostage-taking.
Basically.
If a major car manufacturer doesn't have a secure supply of rhodium, they literally cannot legally sell their vehicles. The cars will fail emissions testing before they even leave the factory. It's not about making a luxury statement. It's about sheer legal compliance.
The demand curve is heavily inelastic. Automakers must buy the rhodium essentially regardless of the spot price to keep their assembly lines moving. When supply tightens even a fraction of a percent, panic buying ensues, and that is how you witness a price spike to $20,000 an ounce.
But their relentless industrial demand doesn't stop at the automotive sector. This brings us to a massive, invisible sector of the market, the tech reliances.
Yes.
Because the modern digital infrastructure, including the very device, the smartphone or computer that you are using to listen to this deep dive right now, relies heavily on the rest of the platinum group metals. Let's pivot to the Rarest report data on ruthenium.
Ruthenium is arguably one of the most fascinating commodities on the market right now because its fate is inextricably tied to the intersection of two massive global forces: the explosive boom in artificial intelligence and the physical limits of global data storage.
This is a connection that feels completely alien to me. How does a rare, silvery transition metal mine from the Earth help an AI system process an algorithm or generate a deepfake image?
You have to follow the hardware chain. Artificial intelligence does not exist in the ether.
Right, it's not magic.
It requires physical data centers. These are massive, warehouse-sized buildings consuming gigawatts of power, filled floor to ceiling with servers. And those servers rely fundamentally on high-capacity hard disk drives to store the unimaginably large data sets required to train AI models.
Okay.
Currently, the entire tech industry is locked in a technological tug-of-war between two data storage methodologies, MAMR and HMR.
I'm going to need a thorough ELI5 breakdown of those acronyms. Let's start with MAMR.
MAR stands for Microwave-Assisted Magnetic Recording. This is the current dominant technology utilized for massive, high-capacity enterprise hard drives.
Got it.
The fundamental rule of data storage is that to cram more and more information, more gigabytes, more terabytes onto a physical spinning disk, you have to make the magnetic bits that represent the ones and zeros smaller and smaller. You pack them tighter together.
But physics eventually gets in the way.
It does. If you pack magnetic bits too closely together, their individual magnetic fields start interfering with one another. A bit pointing up might accidentally flip its neighbor pointing down. This causes catastrophic data corruption.
Which is an absolute nightmare scenario for a multi-billion-dollar AI data center trying to train a model.
Exactly the problem. To overcome this magnetic interference, engineers deposit a microscopic layer of ruthenium, literally just a few atoms thick between the magnetic layers on the hard drive platter.
Just a few atoms.
Just a few atoms. Ruthenium possesses an incredibly rare property. It forces a phenomenon called anti-parallel magnetic coupling.
I need an analogy for anti-parallel magnetic coupling. Help me visualize what those ruthenium atoms are doing.
Imagine two highly volatile, incredibly strong magnets. Left to their own devices, they want to snap together, disrupting everything around them and ruining your data. The ruthenium atoms act like microscopic bouncers at a crowded club. Yeah, they stand directly between the magnetic layers and forcibly turn them away from each other. They compel the magnetic fields to align in opposite directions, standing back to back, so they essentially cancel out each other's interference. This stabilization allows engineers to pack the data vastly tighter without corruption.
Okay, the bouncer analogy makes perfect sense. Ruthenium holds the chaos back. So what is the competing technology? What is HAMR?
HAMR stands for Heat-Assisted Magnetic Recording. It is the highly anticipated next-generation technology. Instead of microwaves, AR uses a microscopic plasmonic laser built right into the read-write head of the drive.
A laser.
Yeah, as the disk spins at thousands of revolutions per minute, this laser fires for a fraction of a nanosecond, intensely heating a microscopic speck on the disk to over 700 degrees Fahrenheit.
Wait, let me stop you. I'm looking at the Rarest data, and this blows my mind. We are basically using tiny lasers to melt a fraction of a hard drive right before we write data to it. How does that not just instantly destroy the disk and everything on it?
It requires miraculous engineering. The material is heated instantly to temporarily lower its magnetic coercivity, making it easier to flip the magnetic bit, and then it cools down in less than a nanosecond, freezing the data in place before the heat can spread and damage the surrounding platter.
That is insane.
Now, the crucial detail for our mineral discussion is this. Achenar platters rely on an iron-platinum alloy, but they do not require the massive amounts of ruthenium that AMR drives do.
So, logically, as the big data centers slowly transition to this new HAMR technology, the global demand for ruthenium should be dropping off a cliff, right?
You would naturally assume that. But the Harris forecast paints a completely different picture. They forecast a very tight ruthenium market, with prices remaining strong between $600 and $975 an ounce.
Why the discrepancy? If the new tech doesn't need it, why is the price still high?
Because the artificial intelligence build-out is accelerating at a pace that is, frankly, terrifying. The sheer overwhelming volume of traditional MAMR drives being ordered and produced to outfit these new AI data centers is vastly outpacing the slow, difficult manufacturing transition to AMR.
Oh, so we just need more of the old stuff while we wait for the new stuff.
Exactly. The explosive demand for the older technology is rising much faster than the new technology can physically replace it. Add to that the fact that ruthenium is also heavily used in the magnetoresistive RAM embedded in thousands of aerospace and automotive electronics, and you have a metal that remains a critical bottleneck for the digital age.
So ruthenium is the invisible backbone of the AI cloud.
Yeah.
I want to shift to another PGM on this list. Iridium. The Rarest report forecasts iridium hovering between an astonishing $3,800 and $5,150 an ounce.
Huge numbers.
That is a massive valuation for a metal that the average person has never even heard of. Where is iridium being utilized?
Well, if ruthenium is the bet on artificial intelligence, iridium is the massive, multi-billion-dollar bet on the future of the green energy grid. Specifically, it is the cornerstone of the hydrogen economy.
Break that down. How does iridium create hydrogen?
It is a critical, irreplaceable component in commercial-scale electrolyzers. The global goal is to produce green hydrogen to replace fossil fuels in heavy industry and transportation.
Right.
To do that without emitting carbon, we have to split water molecules H2O into pure hydrogen and oxygen gases using electricity generated from renewable sources like solar or wind. The most efficient, scalable technology for doing this is the proton exchange membrane, or PEM, electrolyzer.
What goes on inside a PEM electrolyzer that requires a $5,000 an ounce metal?
An electrolyzer has an anode side and a cathode side separated by a membrane. The environment inside the anode side, where the water is actually oxidized and split apart, is incredibly hostile. It is highly acidic, fiercely oxidative, and operates under significant voltage. Almost any normal metal you place in that environment will rapidly corrode, dissolve, and fail.
But iridium survives.
Iridium is one of the most stubbornly corrosion-resistant metals known to modern science. It simply refuses to degrade.
Wow.
The catalyst on the anode side of these PEM electrolyzers relies heavily on iridium black or iridium oxide. Furthermore, iridium is heavily utilized in chlor-alkali processes.
I saw that term in the sources. What exactly is a chlor-alkali process?
It's a massive industrial electrolysis process that involves passing an electric current through a concentrated saltwater solution brine. This splits the saltwater into chlorine gas and sodium hydroxide, which are two of the most fundamentally important chemicals for global water purification, paper manufacturing, and aluminum processing.
Okay, so a very big deal.
A huge deal. The electrodes used in these massive chemical vats are coated with iridium because, again, it is the only thing that won't dissolve in the boiling acid. Its value is utterly disconnected from how it looks. It is valued entirely because it survives where every other element perishes.
This highlights a fascinating vulnerability in the market. What happens when the underlying industries fundamentally shift? I'm looking at palladium and platinum. We established that rhodium handles the nitrogen oxides in car exhaust.
Right.
The sources say palladium and platinum handle the unburned hydrocarbons and carbon monoxide. But if I look out my window, the automotive industry is frantically pivoting to electric vehicles. The traditional internal combustion engine, the ICE vehicle, is supposedly entering a period of terminal decline.
This is where the macroeconomic dynamics become incredibly complex and where surface-level assumptions usually fail. You are correct in the broad trend. Battery electric vehicles, or BEVs, are rapidly gaining market share globally.
Right.
BEVs run on batteries and motors. They do not have exhaust systems. Therefore, a BEV requires precisely 0 grams of palladium, platinum, or rhodium.
So, following standard economic logic, the demand for palladium and platinum should be cratering as we speak, taking the price down with it.
You would think so, but the reality of global manufacturing is significantly more nuanced. First, pure BEV adoption is facing infrastructure hurdles, which has led to a massive, unexpected surge in the popularity of hybrid vehicles.
Oh, right, hybrids.
Hybrids still possess a combustion engine, and therefore they still require a full catalytic converter system. Second, the PGM market is dominated by a phenomenon we call reverse substitution.
Let me try to summarize reverse substitution with an analogy. I read the Rarest analysis on this,
Right.
and it feels like a massive, high-stakes, global game of elemental musical chairs. As soon as the market price of one specific PGM gets too high, the auto engineers scramble into the lab, tweak the chemistry recipe, the wash code, and substitute it for its slightly cheaper neighbor on the periodic table.
I'll take that analogy a step further. It is a game of musical chairs played by multi-billion-dollar corporations balancing on a nice edge. For over a decade, palladium was the undisputed primary metal used in gasoline catalytic converters. But because demand was so high, palladium prices eventually skyrocketed past the price of platinum. So the automakers spent billions of dollars and years of research re-engineering their catalytic converter chemistry to substitute platinum back in place of the expensive palladium.
Because even though it costs a fortune to halt an auto line and re-engineer a global manufacturing process, it is ultimately cheaper than bleeding capital paying $3,000 an ounce for palladium.
That is the raw math of the auto industry. And now, the Rarest report notes a fascinating shift. Because platinum demand has risen and palladium prices have softened, we might see reverse substitution happening again in 2026.
So they swap back.
Automakers might quietly switch back to palladium. It is a constant, ruthless, never-ending balancing act by industrial chemists trying to save fractions of a gram of metal per vehicle. Because when you save a fraction of a gram and multiply that by the 80 million new cars produced every single year, the financial impact reverberates across the global economy.
This incredibly tight reactionary demand loop brings us to the most precarious part of our entire investigation, the geopolitics of supply. We have spent an hour talking extensively about the cutting-edge technology driving the demand from AI data centers to green hydrogen grids to automotive emissions compliance.
Yeah, the demand side is wild.
But what dictates the supply side of the equation? If the modern world needs this silvery powder so desperately, why don't we simply deploy more heavy machinery and dig up more of it?
Because you cannot decouple mineral wealth from the harsh, unpredictable, and often dangerous realities of global mining. When you dive into the data within the USGS mineral commodity summaries, you realize very quickly that extracting platinum group metals is nothing like panning for gold nuggets in a picturesque riverbed.
Yeah, the data on the extraction process is eye-opening. You don't just walk into a cave and find a glowing vein of rhodium sitting there waiting to be chipped away.
Far from it. These elements are found in microscopic trace amounts, tightly and frustratingly bound inside highly complex sulfide ores buried deep within the Earth's crust. To extract them in commercially viable quantities, you have to engage in extreme, deep-level mining.
I want you, the listener,
Yeah.
to really feel the scale of this. How deep are we talking?
Let's look at South Africa. South Africa is the world's undisputed leading producer of primary PGM-containing mine material, specifically extracting from an area known as the Bushveld Igneous Complex.
The Bushveld.
Right. To reach the ore-bearing reefs, mining companies have sunk shafts that go down 2 and sometimes nearly 3 miles straight into the Earth's crust.
3 miles straight down. The logistics of moving humans and rock 3 miles vertically are just mind-boggling.
It pushes the absolute limits of human engineering. The ambient rock temperatures at a depth of 3 miles can easily exceed 140 degrees Fahrenheit.
Oh my God.
The rock itself is radiating lethal heat. To keep the miners from dying of heat stroke, the surface operations have to constantly pump massive amounts of industrially refrigerated air down those 3-mile shafts. You have thousands of miners descending in massive steel cages in absolute darkness. Once they blast the rock, they have to haul millions of tons of this incredibly dense, heavy ore back to the surface.
And the work doesn't stop when the rock sees daylight.
Not even close. You then have to crush that ore into fine dust, process it, and smelt it in massive furnaces operating at temperatures over 2,700 degrees Fahrenheit. Then, the resulting matte is put through an agonizingly complex chemical refining process, dissolving it in acids, extracting specific elemental salts, just to isolate a few precious grams of platinum or rhodium per ton of rock moved.
And every single step of that process, the elevator cages, refrigeration pumps, the massive crushers, the 2,700-degree smelters, requires a colossal, uninterrupted stream of electricity.
Which is the problem.
Right. Which highlights the terrifying geopolitical choke point, because South Africa doesn't just have incredibly deep mines, they have a massive systemic electricity problem.
You're hitting on the central vulnerability of the global supply chain. The USGS report explicitly cites ongoing severe disruptions to the supply of electricity in South Africa as a primary factor decreasing global PGM production.
They just don't have the power.
Right. The state-owned power utility frequently experiences periods where the national power grid simply cannot generate enough electricity to meet demand. To prevent a total national blackout, they implement a system called load shedding,
Which is a polite term for intentional rolling blackouts across the country. I need to pause and trace the logic here because the implications are staggering. If we rely on this specific South African deep mining choke point for the ruthenium running our AI data centers, the iridium enabling our green hydrogen transition, and the rhodium keeping global automotive emissions legal, doesn't a power grid failure in Johannesburg essentially dictate the pace of the global tech economy?
It creates an existential vulnerability for modern manufacturing, yes. When a 3-mile deep mine loses access to reliable power, it's not a simple inconvenience. The massive ventilation fans pushing breathable air stop.
That's terrifying.
The gigantic water pumps that run 24/7 to keep the lower levels from catastrophically flooding stop. The entire operation grinds to a terrifying halt. And you cannot simply flip a switch and restart a deep-level mine when the power returns. It can take days of safety checks to resume operations. This structural instability severely constricts the flow of these essential metals to the rest of the world.
And South Africa isn't the only fragile choke point we rely on. We have to look at the data coming out of Russia.
Russia is the world's leading producer of mined palladium and a major source of platinum and rhodium. Their production is largely dominated by one massive sprawling operation in the Arctic Circle known as Nornickel. And the USGS notes that production there is facing a convergence of severe downward pressures.
The most obvious being the geopolitical fallout from the Russia-Ukraine conflict.
Exactly. Geopolitical uncertainty inherently creates massive hesitation among global investors and thoroughly disrupts established logistical supply chains.
Right.
While some metals avoid direct, explicit bans, indirect sanctions, and financial restrictions make it incredibly difficult for Russian mining conglomerates to source new, high-tech mining equipment or replacement parts from Western manufacturers. The USGS report specifically mentions this lack of equipment access as a major factor hindering their operations.
The report also mentions something called lower metal grades. What does that mean in a mining context?
It means the easily accessible, highly concentrated ore has already been dug up. As the mines age, the rock they are pulling out contains a lower percentage of the target metal.
So they're getting less metal per ton of rock.
They literally have to dig up, crush, and smelt significantly more rock just to extract the exact same amount of palladium they got last year. It drastically increases the cost and energy required per ounce.
So if I'm tracking the macro view here, we have the two largest producers of these critical civilization-sustaining metals, South Africa and Russia, both facing severe, overlapping headwinds that restrict supply. This must create immense price volatility.
It creates a market that is constantly on edge, reacting violently to headlines.
But the Earth's crust isn't the only place we harvest these metals from, is it? We have to factor in secondary supply. I'm talking about recycling.
Yes, and the economics of the secondary supply chain create a truly fascinating, somewhat perverse feedback loop. A very significant portion of the annual global PGM supply, often meeting 25 to 30% of total demand, comes from recycling old, end-of-life catalytic converters, primarily harvested in North America and Europe.
So local scrapyards and salvage lots are essentially functioning as high-grade urban mines.
In a very real mathematical sense, yes. The concentration of rhodium in a scrapped catalytic converter is infinitely higher than the concentration in raw South African ore. But here is the paradox. The rate of that recycling is deeply and inextricably tethered to the primary market price. When the spot price of palladium or rhodium spikes to record highs, say, when rhodium hits $20,000 an ounce, the financial incentive to scrap old vehicles skyrockets.
Because suddenly, the rusty exhaust pipe under a wrecked 2005 Honda Civic is worth $800 in raw metal. Salvage yards aggressively cut them out, process them, and flood the market with recycled metal.
Precisely. But consider the inverse. When the primary market price drops, whether due to a recession or a shift to EVs, the financial incentive vanishes. The salvage yard operator runs the math and decides it's simply not worth the labor cost to pay a mechanic to cut the converter out, extract the toxic ceramic honeycomb, package it, and ship it to a highly specialized chemical refiner.
So you just leave the metals sitting in the junkyard rusting away?
Exactly. So we have this perverse economic reality. When the manufacturing sector most desperately needs a flood of cheap recycled supply to help lower skyrocketing primary prices, the recycling chain booms. But when prices are low and steady, the secondary supply chain essentially strangles itself, cutting off a vital source of metals and slowly building the pressure for the next massive price spike.
It is an incredibly delicate, incredibly reactive web of market dynamics. And it perfectly illustrates the central thesis of our deep dive today. You cannot separate the pristine, futuristic technology in your life from the messy reality of the Earth.
You really can't.
The smartphone in your pocket, the AI algorithm you consult, the car in your driveway, they're all intimately chemically tethered to a 3-mile deep shaft in South Africa, a specialized skarn deposit in Myanmar, and the geopolitical tensions of Eastern Europe.
They are completely inextricably linked. The illusion of a weightless digital future is built on an incredibly heavy, fragile foundation of rare earth and platinum group metals.
Which brings us to our summary and the practical takeaway of this investigation. We set out to deconstruct the true value of the Earth's rarest materials, moving beyond the imagery of gold vaults and diamonds. And what the data has unequivocally shown us is that the title of most expensive has a dual nature.
On one hand, you have the staggering, headline-grabbing, per-carat emotional value of ultra-rare gems. Stones like the imperial green jadeite or the structurally bruised red diamonds.
Right.
The value of these materials is entirely subjective. It is driven by historical aesthetics, thousands of years of cultural storytelling, and the delicate illusion or occasionally the reality of micro versus macro rarity.
It is the $3 million pebble. But on the other hand, you have the consistent, high-volume, utterly uncompromising utilitarian value of industrial elements. Rhodium, ruthenium, iridium, metals that aren't visually appealing, that don't sparkle in a display case, but that are absolutely fundamentally essential to the chemical, environmental, and technological functioning of the modern human era.
And we want to explicitly reiterate a balanced, neutral takeaway here. This deep dive has been an exploration of how technology, geology, and human industry collide to shape the concept of value.
Yeah.
None of this constitutes financial advice. Because if there is one overarching theme our sources make abundantly clear, it is that both sides of this mineral coin carry immense inherent volatility.
The aesthetic market can crash overnight if a lone geologist with a rock hammer identifies a new skarn deposit in a remote jungle, exactly as we saw with the Painite collapse.
Totally.
And the industrial market can crater just as fast if an engineer in a lab figures out a microscopic chemical tweak to swap palladium for platinum, or if the global battery electric vehicle market accelerates faster than the forecasters predict. Value in these markets is never static.
It is a living, breathing thing. It is always shifting, always reacting to the next technological breakthrough or the next geological survey.
So to leave you, the listener, with one final, deeply provocative thought pulled from the fringes of our sources, we have spent this entire deep dive talking about how scarcity drives price.
Right.
Whether it's the cultural scarcity of an imperial green jadeite or the terrifying logistical difficulty of extracting rhodium from the Bushveld complex. But what happens to the concept of price when we look at the absolute rarest verified mineral on the entire planet?
Geologically speaking, that title currently belongs to one of two fascinating anomalies. The first is White. It was discovered as a single, tiny, water-worn alluvial pebble in the B.O.O.G region of Myanmar. It was eventually faceted into a 1.61 carat gemstone. Only one single verified example of this mineral is known to exist on Earth.
Just one. Out of billions of tons of rock on the planet, we have this single 1.6 carat stone.
Or if we descend into the realm of microminerals, there is monapite. Monapite is a mineral that was discovered trapped inside a meteorite that fell to Earth. It is currently known to exist only as a single microscopic crystal. And when I say microscopic, I mean it measures 1 by 2 micrometers.
A micrometer is a millionth of a meter. It is so infinitesimally small, you need advanced electron microscopy just to confirm it exists.
Exactly. So these two materials force us to confront a fundamental, almost philosophical question about the nature of economics and value. When a mineral is so incredibly, profoundly rare that only a single microscopic piece exists in the entire known universe, does it actually become worthless?
Because to have a price tag, to have a financial value, you fundamentally need a market. You need a network of willing buyers and willing sellers. You need an agreed-upon exchange of capital. But if a material is so exceedingly scarce that an exchange is literally physically impossible to create,
then perhaps the ultimate expression of rarity isn't worth a mountain of gold after all. It defies economics entirely. It remains just a lonely geological anomaly, fleeting quietly in the vast, complicated waters of human perception.